In the world of probability puzzles, few are as intriguing as the Monty Hall problem. Named after the host of the classic game show Let's Make a Deal, Monty Hall. The problem is deceptively simple, yet deeply counterintuitive. Imagine a game show stage with 3 doors. Behind one door is a brand new car, a dream prize for any contestant. Behind the other 2 doors are goats, humorous but disappointing prizes. You, the contestant, are asked to pick a door, but the choice is hidden from the audience. Suppose you choose door number 1. The host, Monty Hall, who knows what's behind every door, steps forward. He opens one of the remaining doors, revealing a goat. Importantly, he never reveals the car at this stage. Monty offers you a choice: stay with your original pick or switch to the other unopened door. At first glance, many assume the choice does not matter. After all, there are 2 doors left, so the odds seem 50-50. This intuitive answer, though, is surprisingly wrong. To understand why, we need to step into the realm of conditional probability. Initially, the chance of picking the car is 1 in 3. This leaves a 2/3 chance that the car is behind one of the other 2 doors. When Monty reveals a goat behind a different door, he gives us new information. The probability doesn't split evenly between the remaining doors. The unopened door now carries a full 2/3 chance. By switching, you effectively double your chance of winning. Staying with your initial choice keeps your odds at only 1/3. In 1990, Marilyn Savant famously explained the problem in her column. This counterintuitive outcome has baffled mathematicians, statisticians, and laypeople alike. Readers flooded in with protests claiming she was wrong. Many of them held advanced degrees in mathematics. Yet her solution was mathematically correct. The controversy highlights how our intuition often fails with probability. Let's visualize the problem with a simple experiment. Imagine repeating the game 1,000 times. Each time, you stick with your first choice. You will win approximately 300 times. Now, imagine switching every time instead. You will win about 667 times. The numbers clearly demonstrate the advantage of switching. Understanding this requires distinguishing between independent and conditional events. Your first choice is independent. Monty's action is conditional. Conditional probability depends on prior knowledge or revealed information. Here, Monty's deliberate reveal changes the odds dynamically. Psychologically, we tend to anchor to our first choice. This cognitive bias often prevents optimal decision-making. Contestants, like many people, fear regret more than they value probability. What if I switch and lose? They ask themselves. Yet, regret is statistically less likely if you switch. The Monty Hall problem also serves as a gateway into deeper probability theory. Concepts like Bayesian reasoning and updating beliefs are central here. Bayesian probability involves updating prior beliefs when new evidence appears. Monty's action provides precisely that evidence. In the end, probability isn't about luck. It's about updating what you believe when new evidence appears. That's the essence of the Monty Hall problem.